All right, hi class. Here's the second lecture in the second module. Today we'll be talking about signals and signal conditioning, focusing on resistor-based circuits. So signal conditioning is important, and we're talking mostly about electrical signals here. Most sensors have electrical outputs because electrical signals are easy to transmit, easy to modify, easy to record. So if you can have other sensors, for example, your toilet has a float in it, most of them, to measure the level of the water in the tank. And so that's a mechanical sensor. So if you're trying to transmit that information, you'd have to come up with linkages, modifying some sort of maybe gears or something. So electrical, much easier to do in a small package. So what signal conditioning is it's a way to change the output of the sensor into something more useful for our system. So you can either change the output type. For example, if you have a sensor that changes resistance with its input, you can switch that to a voltage output. That's more in Chapter 8. Signal amplitude, scaling the voltage, is a really common form of signal conditioning, and we'll look at that now. And also filters, where we're looking at the response to a sinusoidal input and removing frequency bands that we don't want. So this is really useful for noise and other reasons. So this signal conditioning that we're starting with has to do with using a switch as a sensor, so an on-off switch. Switches are highly recommended if they can do the job because they are really reliable, easy to tell when they're working, no real calibration required. But there's a common mistake people use when they use a switch as a sensor, and that's shown here. We have our switch connected to a voltage source, and we have our data acquisition system over here measuring voltages. So when we close the switch, we should get 5 volts, and that will work fine. But when the switch is open, when it's disconnected here, most voltmeters will read 0 volts, but most data acquisition systems aren't that, won't necessarily get that response. When the switch is open, this wire isn't connected to anything. And so we haven't determined what it's going to measure on the voltage sensor. It's going to really measure whatever its internal circuitry has. And a lot of simple data acquisition systems like Arduinos will read a 5-volt signal, so you can't tell on versus off. So this is the wrong way to hook up a switch. What you need is to have it always be on or off, connected to here. So this is the most common way to wire up a switch that works well, using what's called a pull-up resistor. We've changed the wiring so the switch is connected to ground initially, and this is most common. You can reverse it. But the way this is set up is if the switch is closed, then we have a short circuit to ground, and so it'll measure 0 volts right here. When the switch is open, instead of a dangling wire here, now it's connected to our high voltage, our 5 volts, through this resistor. So this is going to measure 5 volts. When the switch is closed, it's connected to both ground and 5 volts, but it's short-circuited to ground, or you could look at this as a voltage divider circuit with almost 0 ohms resistance here, so it's going to get 0.0000 something volts, which is going to measure as off. So this makes it so that you always have a known connection to the meter, and you don't have to use 2 switches or anything. So a pull-up is a really common thing. In fact, a lot of microcontrollers like Arduinos, they have pull-ups built onto the chip, and you can turn them on with software. So you can wire up your switch to ground, enable this circuit on the chip, and save yourselves a lot of hassle. So again, voltage on a dangling wire is not determined. You can't tell what it is. You'll get whatever comes out of the meter. Okay, so most of the signal conditioning we talk about here is amplification. So amplification, we have an input voltage going into the amplifier and an output voltage going out, and normally it's scaled by a scale factor, and we call scale factors like this the gain. So if V out is 10 times VI, the gain is 10. So gain normally doesn't have units because it's changing voltage to voltage. But it's also very common to talk about gain in the units of decibels for historical reasons, and it's a logarithmic scale, so sometimes it's a better application. And this just sort of adds a layer of confusion until you get some practice with it. But decibels, for a gain G, the equation is here. You convert it to decibels. It's 20 times the base 10 log of G. So that's just the conversion, and you can change this around to get G back from decibels. So just get some practice with that. A gain of 1, which is no change, is 0 decibels. A gain of 10, 20 decibels, 100, 40 decibels. A gain of 0.1, so we're reducing the voltage, is negative 20 decibels. So if it's negative decibel reading, we're reducing, scaling it down. If it's positive, we're scaling it up. If decibels is 0, we're not changing it. So you'll just get used to this with some practice, but that's what the decibel means. So the most common way to reduce a voltage, if we want to make the output of our amplifier smaller than the input, is to use a voltage divider, because it just takes 2 resistors. It's really simple and easy to do. So we put 2 resistors in series, we run the input voltage through both of them, and we pull the middle out for our output voltage. This is a really easy circuit to analyze using node analysis. So you could do this in one shot, and you'll find that the output is R2 over R1 plus R2 times the input voltage. So this is the gain here in terms of our resistors. So you can choose whatever resistors you want to get the gain you need. So here's an example of a voltage divider circuit reducing this 120 volt input using these 2 resistors. And so applying the formula we just saw, we get an 8 volt output on our output of the voltage divider. Sometimes, well, what's assumed here is that the measuring system, the data acquisition system that we've connected, doesn't pull any current. So there's no current going through here, or else that changes the node analysis and changes the equations. So loading error is when this pulls current that is comparable to the current going through here. So normally this current is so small because this resistance is close to infinity that we can neglect it and it all works out. In this next example, here we've connected up maybe this is a cheap multimeter with pretty low impedance. We'd like the multimeter to be around infinity, and it's really 5,000 ohms. So what we in effect get here, when we measure this, we put a load on these terminals, so that's why it's called loading error. And we essentially get these 2 resistors in parallel now. So instead of our 66.7 ohm, we get these 2 in parallel, which is 65.8 ohms. And if you plug that into the equation, you can see we get 7.9 volts where we expected 8 in our original design. So if you have resistors here on your measurement system that are close to the value here, then you'll have really big troubles with loading error. So it's something to consider all the time. It's one of the drawbacks of using a voltage divider rather than something like an op-amp. So voltage dividers reduce voltages, they make them smaller, and so sometimes people are tempted to use this to make a power supply. So an example might be you need 5 volts to charge your phone, and you've got a 12 volt battery in your car. So you think, well, I can use a voltage divider to reduce that voltage from 12 down to 5. But the problem is when you're using that as a power supply, then the current going into your phone is not close to zero, which is what we've assumed for all of these. So it's an application that does the worst in terms of loading error. And the great news is there's a very simple part called a voltage regulator. It's a 3-terminal part. They cost about $1. 7805 is the classic one. And there are 3 terminals. You give it the input voltage, you give it ground, and you get an output voltage at the voltage that you want. And these have active circuitry. There are a bunch of parts inside that are actively changing things to maintain a constant 5 volts, whether your input is 12 or 13 or 11. They're very inexpensive. You'll also see DC to DC converters, which are essentially the same concept, a little more efficient and a slightly different way to get it done. But that's what you'll find in most phone chargers these days because they don't get as hot. So a voltage divider scales the input. It doesn't create a constant output, which is what you want for a power supply. We want to scale the input for things like sensors, though. So use the voltage divider for a sensor. Use a voltage regulator if you need a constant reduced voltage. Here is another example of using a voltage divider for a battery monitor. So if you have a 12-volt battery and you want to know, is my battery going dead? What's the voltage? And you want to hook it up to an Arduino to measure that voltage. The Arduino has a maximum input voltage of 5 volts, and if you give it more than about 7, you'll tend to burn the chip out and damage it. So with a 12-volt battery, the kind that you'll find in your car, ranges typically from 0 to 15 volts when it's charging to when it's dead. So we want to divide that by 3 to respect the 5-volt maximum that we have. So if we choose these resistors, a 2K for R1, a 1K for R2, we get that the V out is 1/3 VI, and that's a good solution for measuring the battery voltage. Now something with voltage dividers, you can multiply both resistors by a constant. So this could be 200 and 100, 2,000 and 1,000, 20,000 and 10,000, and you get the same ratio here. So you get to basically choose one parameter here. And you might choose this to minimize the battery drain. If you hook your battery up at VI, it's going to constantly be running down. So these values are going to keep the total resistance to 3,000 ohms. So you'll get milliamps draining from your battery. That's not bad. If you want to make the resistors really large to minimize the battery drain, then you have to start worrying about loading error because you'll have a really large resistor over here too. So it's a trade-off, but you can usually find something that works. All right, so that was the summary of the resistor circuits we used for signal conditioning. The pull-up resistor, if you're using a switch as a sensor. The voltage divider reduces voltages in a really easy way. We also looked at the voltage regulator. It's not really used for signal conditioning, and it's also not a resistor circuit, but it came up because you shouldn't be using a voltage divider when you need a voltage regulator. All right, I will see you in the next video.